Hey everyone, how's it going? Welcome to the stream. So tonight's going to be probably a shorter stream than last time. But yeah, I just wanted to see if I could figure out this joystick stuff that I started looking at a couple nights ago. So hopefully I'll make some headway tonight. Yeah, I didn't get a chance to actually look at this since a couple nights ago, so just continuing where we left off. So yeah, basically what we're trying to fix, just to kind of summarize, we have a couple games. Let me see if I can, over here is it? My compatibility list. So yeah, we have a bunch of games tagged analog no center, where these are games that actually hold the analog stick on the Vectrex and look for more than just a left, right, or center value. They want to see are we like how much are we going left, how much are we going right, let's say, or up or down. So pole position is a game, it's a racing game. Here it's going to be pulling left to right to see like how much to turn the car or move the car left or right. Solar Quest is another game that has this problem. In Solar Quest, basically the ship is constantly turning, so it uses the analog value to decide how quickly to turn. Starhawk, I think, is similar, so we have a few games like this. So we want to fix those. I've been testing pole position. I can actually show that here. Yeah, pole position. So say we run it. And we fast forward. I'll just minimize this. 4, 3, 2, 1. Okay, so here we go. So basically you see if I go left and right, he'll face right. If I go left, if I press no input or left, he'll face left. And basically what we want is that when I press no input, he should be facing straight. But that never occurs. In fact, I should probably try just to see what happens if I actually put in a proper analog joystick. But I'm pretty sure there's just nothing I do. Yeah. So it's actually interesting here. Here basically, if I touch a little bit to the left, it points left. And I touch a little bit to the right, it points right. But never points in the center. So that's kind of interesting. Huh. That is actually interesting, isn't it? So, okay. Let's see if we can use this information to help us. So we were looking at the function that manages this is, where is it? Here. So in the BIOS we have this function called joy analog. Also joy digital it gets called. It's the same function. It's just that joy analog starts a bit earlier in memory, and it ends up setting a flag that says we're about to do this, but for the analog inputs rather than the digital inputs. And then yes, I was trying to understand this code, and I must admit I don't fully understand it. I did find one thing. So I found this. This is a documentation that I was looking for last week, which is on the malban.de site, which is a site that has excellent Vectrex information. And so here it talks about reading the joystick, and it talks about it at the lower level. And so yeah, basically it talks about exactly what we were looking at, which is, at least what I've understood, is that you have the DAC, which is register A on the VIA. You have this multiplexer, and it uses the mux to select which joystick input we're looking to read. So for the Vectrex, you have up to 2 joysticks you can connect, player 1 and player 2. And so basically here, port 0 would be, let's say, the player 1, and port 1 would be for player 2, and here you have the 2 directions for the analog stick. So If you put 0, 0, or 0, 1, it means you're looking to read horizontal and vertical values for the first joystick. And otherwise, if you put 1, 0, or 1, 1, you're looking to read joystick values for the second joystick. And I handle this, right? Like if we look, this is what we can see when we go in here in the VIA, and we figure out here, like, is the mux enabled? If it's not enabled, so this is a bit of a, maybe confusing. We are still using the mux, but it's an enabled bit that says what is the mux actually connected to. In this case, if this bit is off, it means that we want to read the values from the joysticks. And then here we say figure out which joystick. So that's what the mux selection here is, and it's going to be 0, 1, 2, or 3 based on these values. We're going to get 0, 0, 0, 1, 1, 0, or 1, 1 here. And then that's what we use here to read from the joystick analog state. So if you look at this, the joystick analog state is basically 4 values. The first 2, it really corresponds to this. So great, right? Now, if we continue reading, it says here, the circuit compares the value of the potentiometer to the analog value received from the DAC. Okay, so the potentiometer is basically like what's in the joystick for the analog stick itself, and the DAC is register A. So this is port B here. We're talking about register port A here. So that value, you see here, this is a read, but actually for the write, we want to go look at write. When we write to port A, we just store a value in port A. That's it, right? So that value is what we compare as a signed value up here. Back when we start reading, we're going to take port A's value signed. So that's what this cast does here. And then we're going to say, if that value is less than the potentiometer value for the joystick, which again is a signed value as well, we set the comparator bit. So think of port A as it says here. Here it says, if the contents of the DAC, the analog representation of a digital signed value ranging from -128 to 127 is smaller than the value gotten from the potentiometer, then the above mentioned pin is set to true. Otherwise, it's false. Right? So that translates directly into the code I wrote here. It says we take this value in port A and we set the comparator bit to true if port A signed is less than the signed value of the potentiometer for that joystick input. So, what else? The pin, how could it be otherwise, is again part of VIA. It can be found in VIA port B, bit 5. So that's exactly what we're setting here. Port B comparator, this is actually bit 5. Here we go. The bit pin is cleverly named comparator input bit, meaning input from the comparator, not input to the comparator, sure. With that information, a digital request in pseudocode can be done like, question, is joystick port B moved to the right? So we want to know if the joystick, the second joystick, so port B, is currently facing right. And then it tells you what to do. You disable the mux, you set a value of 0 in the DAC, so that's port A. We set the mux selection to 0, 0, which actually I wonder why. Is joystick port B? I don't know why he says joystick port B here. I think he meant port 0. Anyway. And then he's going to check 0, 0 because that's horizontal, right? Because that's what we care about. So let's say it's basically, is the port 0 horizontal currently right? Enable the mux so that it reads the value. We delay a little bit. We disable the mux. And disabling the mux is what allows us to read back joystick values. We delay long, whatever. This is hardware stuff, just to make sure that the hardware has enough cycles for these state changes to actually take effect. Not such a concern in the emulator where we don't have these kind of wait cycles, right? We just kind of immediately, these for us, doing this has an immediate impact. Delay long, okay, load the DAC with some positive value. Yeah, actually I was wondering why I set this to 0 here. What does that do? You just go take a look again in the write function. Maybe it's for update integrators. Not sure why you'd have to set it to 0. Disable ever set the DAC to 0 here, I'm not sure. Anyway, but the important bit is here. So you load the DAC with some positive value. Now, since we're looking to see, bring this here. Okay, so like what we're asking is, you know, are we moving right? So if we think about our range, minus 128 to 127, you know, and where 0 is in the center, right? So it's like that. We're moving right if our value is somewhere in between 0 to 127, right? So let's say we chose 64. So if we write 64 in our DAC, as long as our joystick potentiometer its value is greater than 64, it's going to set the comparator bit to true. That's basically what the comparator bit is. So you can think of it like kind of like a line, and you can move it along this axis here, you know, and like the potentiometer bit will be, sorry, the comparator bit gets set as long as the current value is to the right of the input value for the DAC. So we load with some positive value, we check the compare bit, and if it's set, that means the joystick was moved right. So here we go into an example. To get an analog value in principle, the same must be done. So here he's saying to get an analog value. So here, I guess he's saying if you want to go into a more precise thing to do. So this is kind of like a very simple test we can do to just say, are we right or not? But if we want to know how much right we are, what we want to do is we want to do multiple tests, right? So let's say we want to know, like, are we moving to the right? We probably want to start by saying, well, first, you know, are we greater than some value, perhaps 16, and then 32, and then 64, you know, and so on. Maybe 96, 120, well, I guess that would be the end of it. So it says here, to get an analog value, in principle, the same must be done, but you have to test more. The line load DAC with some positive value, and the checking afterwards has to be done with increasing values till a point is reached where the flag is not set anymore, right? So if we come back, let's say our axis value is actually keyboard is actually, let's say we've gone right with our analog stick and we're at 70. So we start by checking, you know, we enter a value in the DAC of, let's say, 16. Well, the comparator bit will say false. Then we put 32, it'll say false. 64, it'll say false. Say 96, oh, now it says we're true, right? Which means, oh, sorry, that's not quite true. 64 is, yeah, no, sorry, that's right. And then 96, it'll say we're true. And then if there's no more to check, well, maybe I'll change this value because it's not a good explanation. Let's say I put 50. So when we get to 64, this says true, but we're not done yet, right? We have to keep going to see just, you know, we continue. And then we say 96, and this is false, right? So we know it's somewhere between 64 and 96. So that right there, you know, we can return then this information. Perhaps we return like a bit or something, and we say, look, this is how far right. And that gives us some granularity, right? Some number of values we check against, and that's our analog value. And so our game can, in this case, decide to make the car turn right more based on which one of these we get. Although, to be fair, I don't think it would be 96. But let's just see. This is why it is usually a good idea to only use analog values if it is absolutely necessary, since it is time consuming to do the approximation. So here's a real life example of a digital joystick request for port 0. not the BIOS function. This is so this example kind of shows what he calls it digital, meaning just checking if it's greater than some value. And a lot of this looks similar to the BIOS routine. Unfortunately, it would have been cool if he had given a real example of like slowly incrementing and especially going, let's say, checking for left values. But still, we can kind of deduce what we're looking for from this. So the important bit, so we got some query stuff. Let's see here, some setup. Mux disabled, mux selection, vertical port 0. Let's see. Mux enabled. Okay, so there's a wait loop. The interesting bit is coming down here. Load B with comparator bit. So this is what we're going to be checking against. Like bit 5, we want to know if a comparator bit is set. So we're going to use B for that. We're going to load A with some test value. So here is 40 in hex. So we're going to be checking. So I think that's 64. Yeah. So we're loading the value of 64 into A, and then that gets stored into port A of the VIA, and that's our DAC. So that we put the test value in the DAC. Then we load A with 1, so the default result value Y. Was it the default result value Y was pushed up? I don't know what that means. And then bit B, so here we check, is the comparator bit set? So we're checking bit 5. Now if it is, it means that our joystick is greater, its value is greater than 64 decimal. So branch if not equal to read done. So if the comparator is not cleared, it means it was set, the joystick was moved up. Oh, okay. So I see what he's saying here. Basically, we're actually looking for a vertical movement here. So we're looking to see if the joystick was moved upwards, not horizontally in this case. So that now I understand this mux selection of 01 here. We're checking if the first joystick's vertical is up. So that's why we say if the comparator is not cleared, the joystick was moved up. So branch if not equal to Y read done. Otherwise, load with a negative value. So here we're going to check for down. So if it is true, we're done. So if it is up, we're done, and we return 1 to say, yeah, we're pointing upwards. Otherwise, we're not done, and we negate the value in port A. So now we go put minus 64 in there. Also switch to possible results. So this 1 becomes minus 1. This is just the result of the function, right? And now we test against we test the comparator again. So this is interesting, right? We want to check. Let me think about this one for a sec. So if we put minus 64, I guess this time it's the other way around, isn't it? It's not now. If the bit is cleared, it means our joystick is to the left, right? Because if it's to the right of it, the bit would be set. So, and actually, when you're looking for negative values, so let's say left or down, we want to check to see whether the bit is not set, to know that the comparator bit is not set. So we test comparator, but this time we say branch if equal to done, not branch if not equal to done. See, if cleared, the joystick was moved down. Okay, that's important. If it's still not cleared, so if we didn't do the move down, it means that we clear A as the final vertical. So that means that if we reach this line, the joystick is neither up nor down, but somewhere in between minus 64 to 64. So probably just in here, right? Probably 0 or near 0. So it says if it's still not cleared, we clear A as a final vertical test result. No move at all. So that's what clear A does here. So that's it. So basically, if we're going to go up, A will have 1. If we are pushing down, A will have minus 1. Otherwise, A will have 0. We're done. We store that into some memory value. Remember the result. And now we do the same for horizontal. So yeah, so you see we set 0, 0. Yeah, I'm really wondering about this clearing of the DAC to 0. I wonder why that's so important. But anyway. Decrement B, so B mux enable, okay, wait, increment, disable mux. All right, and then once again we load B with the comparator. We put 64 positive, so we're going to be checking for right. We start on the DAC. We say we probably are moving right. By default, we say 1 if we move right. We check if it's true. If it's not equal, we're done. If it is equal, it means the comparator bit's not set. Now we check for left. So we negate, so minus 64. We put -1 in A, and we check against the bit. And this time, if we are equal, it means that the bit isn't set. So if it's clear, the joystick was moved left. Or we clear A if we reach here. It means we're not left or right. So it's same exact logic except in the other direction. So see, I get this code, right? This code makes a lot of sense. It makes more sense to me than this code, which is the code that will do the sort of incremental. Maybe with that in mind, I can try to understand this code a little bit more. So let me see. So joy analog, set the analog mode flag, point to the first pot. So we load X with joy mux 1X. So that means we're going to be looking at joystick 1 in the horizontal direction. So that's the first thing we're going to be doing, because we see I have 1X, 1Y, 2X, 2Y. And we're going to be doing this for each one of these. You see? Load X with this. And then read it if enabled. So, okay, so the next thing we do is we load into A the value that is at the address of X, so the value from here. So let me just read something here. What exactly is expected to be stored in this address? Joystick 1X enable mux flag. One, 3, 5, and 7 was it? Not sure I understand. What is it? I wonder what it uses this for exactly. Why is it 1, 3, 5, and 7? One, 3, 5, and 7. No, sorry. 1, 3, 5, 7. Not sure. So it says enable, then it says mux flag. So it looks like, it sounds like you would want to set a value in there to know whether you should bother querying it or not. And specifically, you would want to set one of these values for the joystick. 4 bytes here, right? Okay. All right, so, okay, so let's say we want to check the first one. We load into A its value, read it if enabled. So I guess if it's 0, that means that branch if not equal. Right, so branch if not equal means that it would actually have a value in there. Otherwise, we say go back until all pots are red. So is X equal to C823, so the last one? Is that right? Branch if not equal, so we go back and we load the next one. So this is basically the loop to check each value, each of the 4 bytes that contain those flags. Those apparently enable mux flags. Okay, fair enough. But anyways, in our case, we are going to have a value in there because we want to check. Like the game wants to check mux 1x. So we are going to jump here. So enable mux and select the pot. So store the value of A, so that is the mux value, into port B. So enable both the mux and specifically which pot. Okay, so actually... Okay, that actually, now I think I understand. This comes back to the which bits need to be set. So it's bits 1 and 2 that need to be set along with the enable bit, right? Okay, I understand now. So what we saw, yeah, okay, this makes sense. We come back. It's just confusing because, you know, here 1, 3, 5, and 7. So all of those basically have bit 1 set. Now 1 is basically, well, if it's 1, it means we want 0, 0. So look at bits 1 and 2 over here. Bit 0 has to be enabled to enable the mux. And then the mux which multiplexer value will be 0, 0 for the first, for let's say the X direction of joystick 0. Otherwise, it's like this for the Y direction, so that's our 3. Otherwise, it's 1, 0, which is the X for the joystick 2, there's our 5. Or 1, 1, which is 7 for the Y direction of joystick 2. So that explains these values here. So great. So we use that value in A and store it into port B to enable the mux and select the right pot. We output 0 to the DA for whatever reason. I really do wonder about that. Why we have to do that. It's not really explained, and I don't really care about it. And I'm wondering if that's important. Because I am going to call update integrators. And only if the mux is enabled. Otherwise, we end up setting the x-axis integrator to 0. So I'm not sure if that's important to us, but whatever. Let's keep that in mind. We disable the mux at this point. And that's important because we need the mux to be disabled for to be able to read back joystick values. So if we come back into the read function for port B, you see if the mux is not enabled, now we are able to read joystick values. So that's what this is about. Then we need some kind of delay. So here again, this is what we saw last time. We load B with 60 in hex, and then we keep incrementing B until the value branch if positive, which means it'll check to see if the negative bit is set. The negative bit will not be set because it's a positive value, so we're going to keep looping back to up here. So we're just going to keep executing these instructions until B contains 80. And what that means is that that's when the negative flag will be set, because this is 80, right? So that's the bit that sets the negative flag. So just as it says, delay and end up with B equals 80. Sure. Now, we get to here. So at this point, B has 80 in it, right? Now we load A with a value in C823, which, by the way, up here, you know, that's where joy analog, when we jumped here, we decremented whatever value was in there, which meant set the analog mode flag. And so here we say branch if analog pot. So I think what this is that this is usually 0. Then we decrement it, it becomes -1, let's say. And then we check if branch if minus to here. If instead we had just come to joy digital, that value would have remained 0. So then we would not have branched to LF240, and we would have continued down here and done the digital test, which would be the faster test, right? In fact, let's see what would have happened. because actually that's what most of our games are going through. Almost certainly most of our games are just doing a joy digital, which is why they work. So let's see, let's just understand if this code makes sense to us, right? So this is really like the digital input test here. So we load our comparator test bit into A. We increment port B to enable the mux. So why exactly do we do this? That's rather interesting. Enabling the mux is a bit of a surprise here because that's not going to actually increment port B to enable mux. But if the mux is enabled, we are not going to actually set this thing correctly when we read from it, right? Let me split this here. We write to port B. We will update integrators. Mux will be enabled, so we'll end up doing this stuff here, but that just sets like velocity, offsets, brightness. None of those things are important to us right now. Why would it enable? And then we test comparators, so this will read from port B with the mux enabled. Okay, I must say this is a little bit surprising. How this even works, I don't understand. Yeah, the mux disable, it really is bit 0. If it's set to 1, it means the mux is disabled. I think this comment may be incorrect. If we store a 1, we do indeed disable the mux. That's true, because it is a mux disabled bit. Then oh no, we don't reach here. We actually go here. We store value in A to port B. We saw that that was a bit set in the last. So I think this is not correct. This should be disable mux and select pot. This is an incorrect comment. Let's just say disable mux and select pot. If the bit is set, and we saw that it is in those values for vecjoy mux 1x and all that, that should disable the pot. I feel like I've already gone through this code like a few months ago and I did exactly this correction, but for some reason I don't have it here. So we disable the mux and we select the pot. The output 0. Now when we decrement here, that actually enables the mux. We delay, right? And then when we increment, this goes back to disabling the mux. And now we can test the comparator. See, this makes more sense. Yeah, these comments don't really make sense. Unless what they mean is enable the mux for joystick, right? But technically, we are checking the disable mux disable bit. So that's why it's very confusing to say it that way. It's kind of like there are two muxes. Right, there's a multiplexer to control the beam movement, right? The integrators for the beam, and then if you set the bit to disabled on, then it's like the mux is now connected to the joystick stuff. So I think that's what this code is trying to say, but it confuses me to think about it that way. So to me, disabling the mux means we're now connected to the joystick stuff. So we test comparator. So yeah, so what are we testing against? What is the value that was stored in port A, actually? We put 0. Okay, so we put 0 into port A. So when we do the test, that means that if the comparator bit is set, it means we are going to the right in this case. At least the very first time, right? So we check to see if we are equal to LF22D. Otherwise, okay, so I guess branch if equal would mean, what would it mean? It means the bit is set. So if the bit is set, we are to the right of 0. The comparator bit is set, we're to the right of 0. So we would come here, and now we output C0 to the DAC. Instead of 0, now we're going to test C0. Let's see. So 192. Okay, so a fairly... Does that make sense? Oh, this would be a negative value, wouldn't it? Yeah, minus 64. All right, so let's see here. Test comparator. So branch if equal, so does that make sense? When we do this bit A, we're checking this, flag to check if that bit is set. If it is set, we are equal, right? Which would mean that the comparator bit is set, which would mean that we are to the right. That's what I would have expected. So why would we check to the left if we know we are to the right? Let's see here. And then here 40, that's our 64. Oops. I'll just use the same nomenclature. So ostensibly, if we're reaching here, it's because we think that we are check if to the right or up of joy value. And then here should be check if to the left down of joy value. Oh, right. Okay, yes. Sorry. I'm getting confused because of the branch minus from the other example. It's not branch minus. Okay, we're checking branch if equal, which means we're checking if the 0 bit is set. Right? That's the confusion. It's always confusing for me. Basically, we're equal if 0 is set. Because equal means if you were to subtract two things and the difference is 0, that means we're equal, so the equal bit is set. So anyway, so what this means is we checked and we would branch to LF22DD if the comparator bit is not set. So joy is not right or up. Or I should say here, basically, joystick value isn't greater than or equal to 0. Let's put it that way. Because if it is, now we're going to see, like, are we right of 64? There we go. That makes more sense. Check if joystick value is, so check if joy value is greater than or equal to 0. Check if joy value is greater than or equal to 64. And check if joy value is less than minus 64. Let's just say left down. Okay, so that makes more sense. And then the result is always in B. So we can see here that B was loaded with 0. Where is it? Actually, okay, yeah, interesting. We increment B here, right? So this makes B equal to 0. So this, because B was 80, right? So we by incrementing it now, it becomes 0. So that's actually super important. Why did I think it remained 80? I need to double check this assumption of mine. Because see, it makes sense, right? Oh, no, sorry. What am I saying? We keep incrementing B and branching, okay, until it becomes 80. So then when we reach here, it is equal to 80. Now, if we're not analog, right, we are continuing down here. We load A with 20, increment this. Oh, right, that's it. Because what actually happens is if we see that we are, if the joystick value isn't greater than or equal to 0, we jump to here. Otherwise, we're going to check here to see if it's greater than 64. Now, if it's not equal, we're done. Otherwise, we go here. And there's the clear B. This code is very confusing. So this means if it is greater than 64, B will contain a value of 64. But if it's not the case, we jump to here where we clear B. And then that's the B that we store. So the result of all this is that what we store is either minus 64, 0, or 64. That's the result of this function. And I think that's exactly what it says up here. It just says less than 0, greater than 0. But we know now the exact values that will be stored there. Okay, so that explains the digital test. Now the test that we're interested in for these games is the analog test, right? So that's going to happen over here. Check the analog flag, branch of analog pot. So it is going to be set. It's going to be a negative value. So we're going to jump to here. And then as we said, when we come here, we should have 0 in port A of the VIA, port B of the VIA should be 0 as well. B should be 80, and A should be FF, but this gets set to 20 right away. Yeah, right here. Okay. So let's see if we can make some sense of this. We end up testing the comparator. We know that the first test is going to be checking against 0, just like in the digital case, right? Because port B was loaded with 0 before we jumped here. So let's see if that's true. No, sorry, port A was set to 0 right here. So that's it. We cleared port A, and we ended up jumping here. So the very first time, over here, so first time, as we said, port A is equal to 0. So first time we check if joy value is greater than 0, greater than or equal to 0. Now, branch if not equal, so thinking again about that, if it's 0, it will be set to equal. Yes. So not equal means we're negative. That's why it says branch to go lower. Branch of bit is set, meaning port A value is less than joy value. So I did actually figure this out last time. Okay. Because if it isn't, this code, and this is the part that I don't understand. This code, I wrote this code undoes the code above that sets the test bit and just brings it back to 80. Yeah, there's something here that doesn't make sense, what I was thinking. Let me see if I can make more sense of this. We transfer B to A. Now what is in B and what does B represent to us? B represents the value we want to return, right? But see, B would have 80 in it. That was what's really confusing about this. Then we do this exclusive OR. To port A, and then we store the value of A. What would we want to do? Normally, if this is not the case, it means that our value is either greater than or equal to 0. And we want to check probably the next positive value. That's what we would want to do here. I think the key here behind this exclusive OR and this little trick is about keeping the negative bit flag. I think that's what this is about. It's this clever code for writing the code once for us to be able to check iteratively against negative values or positive values. I think that's why we do this exclusive ORing here. We know when we come in, B is 80, right? We know that that means that it represents a value of minus 128 initially. And that's what we transfer into A. When we do this exclusive OR against a value of 0, we still remain with minus 128. We store 80, so minus 128 into here. Okay, exclusive OR A means get the value here, do an exclusive OR against what's already in A and store it back into A. So, I think what this is all about is, if this bit were set, it remains set. If this bit were not set, it would be clear. It would not be set into A. I think that's what this is about. This is about, do we keep the top bit set or not? The negative bit. That's what I think this is about. So let's see if that makes some sense. Branch if bit is set, meaning port A value is less than joy value. So actually, right, I wrote joy value because the first time it's 0, but after that the joy value keeps changing, right? Okay, so first time it's 0. We're going to check to see if we branch, it means that our value is less than 0. If we don't branch, it means it's greater than 0. We transfer 80, we do this exclusive OR, we store A back into port A. And then we come to here. Try the next bit position. Logical shift right B. So the 80 will be shifted right and will become 40. Check for accuracy threshold. So this accuracy threshold, this is a single bit, so it's a power of 2. That if you set it to 0, it means we want full accuracy. So this is kind of like, when do we stop, right? So if we set to 0, it means we're going to want to run, I think it means all 8 times or say 7 times. If you only want it to run, let's say 4 times or 3 times, you will set it to 8, let's say. So that's what we're doing here, is we're comparing. And I think in our case, it is 0 when we compare here. So then we continue. So go back if not finished. That is our case. So what happens? Now B would have 40 in it. We go up here and we transfer that 40 into A. Interesting. So actually this should be 40 goes into A. Now we OR the value 40 with what's in port A. And again, I think this is about, yeah, turning on just a bit we want to test and maybe keeping the negative flag, which is what, it's a bit weird, right?
Wake up, Link.
Because you see, anyway, what I saw was like, it's like we're testing against C0, then A0, then 90, and that doesn't really make any sense because these negative values, it's not a, Doesn't make any sense. I mean, it is ever increasing, but strange, right? 124, 126. It's like it's a curve. It's so strange to be testing like that. That doesn't seem reasonable to me. Otherwise, we'll be checking 64, then 32, then 16. So I don't understand. I have to look at the numbers. Maybe if I look at the numbers, it'll make more sense now. Turn on the bit we want to test and store it into A. And then once again, test the comparator, we test it, branch to go lower. Otherwise, transfer B to A and then do the exclusive OR again. To get back whether that bit was set or not. Top bit. So I think I saved the trace. Did I save it somewhere? I did. Let me see. Yeah, it was this. This was the trace from last time. Let me see if I can make some sense of this. L240. So let's go to so that's our first bit A. We would branch if not equal to F24C, which is not the case because it's 0 the value, so that's what I expect. Now we do transfer B to A, which means we put the 80 into A. We do exclusive OR of A. Oh, wait a minute. Exclusive OR A, the value that's in B. Is that, did I understand that? Oh, no, sorry. Value in A, yeah. So port A, that's true.
So, you're finally
Yes. Okay, yeah, exactly. So read back the value in the DAC, exclusive OR, with what is already in A, which is 80, and we still get back 80, because it's 0 exclusive OR 80, so we get 80. And we store 80 back into that. So now the DAC has 80 in it. Does that make sense? Yes, it does, because we are going down the branch of testing for negatives. We saw that it is not greater than or equal to 0, which means it's not a positive value. It might be a negative value. No, sorry. We saw that it's not greater than 0, not greater than or equal to. True. So now we're going to test to see if it's negative. I was putting equals, but it's not equal. It's just greater than. B becomes 40. What is this again? Compare B against this. Okay, so this is what I was saying. This is the resolution we're looking for. So 0 is the highest. So we're going to be doing this shifting up until B becomes 0, right? So we don't branch. Or actually we do branch to F23A. Which means we go back, now we go up here. This is the first time we go here, at which point we transfer B to A. So now we get 40 into A, right? And then we do this ORing of whatever is in A with the thing in the DAC. So the thing in the DAC is 80, and now it's going to become C0. We're turning on the top 2 bits. So like this. So that means that we've just basically now put minus 64 in the DAC at this point. Okay. Now we load A with the comparator bit test flag, and we check, is the comparator bit set? So we're at F242. We're here now. And we say branch to go lower. So again, if we're checking against, I'm saying if we're to the right and branch not equals means comparator bit set, right? So we take, but not sure about this. We're going to be checking this bit mask against what's in A, which is, sorry, what's in the, against the comparator bit. Now, if the comparator bit is set, that means that it's 1 and 1, which means that 0 is not going to be set, so 0 is false. So we branch if not equal. Branching and if equal would mean that the 0 was set, branching and not equals. So I would have expected to actually branch here, but we don't. So maybe that's our bug here. So let's actually debug this properly now. Now that we have a bit of a deeper understanding of this code, let's put a breakpoint on F240 and let's actually step this. Okay, so I have the optimize off there. It's good. Hit our breakpoint. Let's disable that until we actually have our car there. So here's our breakpoint. I should have waited for that one. So let's see here. We're going to say is the comparator bit set? And it's saying no. You know what, I'm gonna end to save. Okay, so let's see here. Let me read. What is it again? It's oh, print. So there's 80 in there. 0 and B. So our DAC has 0 in it. Okay, so the next thing I'm going to do is I'm going to put a breakpoint in the read of port B, which is the next thing we're going to do. There we go. So what does port B have? It has 128. So the mux is enabled. So we're not going to actually do this correctly. That's true, we don't have the bottom bit for port B set right now. What's the deal with that? Huh. Oh, that's interesting. So the mux is disabled when we store our value here, which is correct. Not here, but actually over here we say store A into port B. This disables the mux and selects the pot. But then we do this enable of the mux. And then the thing is, we saw for digital, we re-disable it by incrementing port B. But when we don't go into the digital branch, we do check analog, and we jump to L240 down here, we don't do the same thing with port B. We don't disable the mux again. Which means that whenever we're checking the comparator bit, it's not actually checking it at all. And that's indeed the bug. At least that's why it's not working. We're not actually getting, we're just getting whatever stale value was set in there. Isn't that correct? Like, do we ever hit this breakpoint here? Oh. Port B. So now port B does have 1 1 on the bottom. What led us to this? Oh, it's hard to know, isn't it? Because we just ran until the next breakpoint hit. What could have caused that? I guess we could do this again. We'll put a breakpoint here. We'll continue. We're in the process of doing a deck. Let me see if I can get what instruction we're at. Is there a way for me to know easily what we're doing? Oh, I know. Let's check with what the yeah, let's go check what the PC is. F4A7. Yeah, definitely not in here. So what are we doing? Oh, we're doing a print string. Right. So yeah, so I'm right. So we aren't really ever getting in there. So then what, did I like misunderstand how this works? You remember how the integrators have access to the DAC values? The DAC value goes through a multiplexer. The multiplexer has two select lines, port bit 1, port B bit 1 and 2. The select values multiplex the one input signal to one of 4 output lines. The output line is chosen by the value of the select lines. Why am I telling you that? Because with the joystick potentiometers, this is the same, really the same. Since the physical electronic part inside the Vectrex is the same, that chip is a multiplexer, demultiplexer, the same select lines. Select which of the 4 potentiometers it takes as input. The multiplexer sets the voltage one selected. But it doesn't say how it gets selected here. But we see it, right? Disable mux. And then disable the mux to then do the read. This is important. Disabling means setting the bit on. This is like crazy. So, okay. Let's try something. Let's try not even bothering to check if the mux is enabled. Let's say that since the multiplexer is let's just assume it's always connected. I mean, I don't really understand it, but let's say we just don't check this. So that just means we'll be setting the comparator bit when we read port B, even in the case where the mux is enabled, which would maybe fix our problem, but I don't understand it. At least it doesn't seem to match up with my understanding of what the docs say. I got the impression that the multiplexer, 4 lines, choose one or the other depending on that mux enable or disable bit. But maybe I'm wrong. Maybe it's always reading joystick values. Let's see. Oh, you look at that. Huh. It's not quite work. Is it working? Yeah, it is actually working. Yeah. We can see that there are multiple, like we can just do a little move or a big move. I'll pause the game and minimize this. Wow, it's cool to finally be able to play this. Looks like there's only 2 gears. Gas, first gear, second gear. Well, that's very interesting. So for integrators, definitely the mux needs to be enabled if we want to write to integrator values. But it seems that for analog input, we don't really give a crap about this. And what is all this about? Disable the mux, write these values, enable the mux. Disable the mux here, and it is indeed what happens for digital, but seems completely unnecessary for analog based on how the BIOS code is written, right? Yeah. See, here we have it, the increment on port B. That's the disabling of the mux. That sets bit 1, or bit 0 I should say, of port B, which is disabling the mux. Why? Ostensibly it's because that means you're going to be testing. I thought it meant that the 4 lines are going to be now redirected to reading from the joystick pots as opposed to reading from the actually, does it ever read? For writing, it makes a difference for sure. Like here we have in write, we see that when we write to port B, we want to update integrators. Same thing if we write to port A, we want to update integrators. But only if the mux is enabled. So it does seem that the mux enable bit will either allow or disallow writes to the integrator values, right? The y-axis integrator, xy, z-axis, all of these. However, in terms of reading from the joystick pots, it seems it's not important at all. Which doesn't make any sense. It doesn't make sense. The reason why I say it doesn't make sense is because even in the BIOS code, so apart from the fact that it does it for digital, we also notice that these values for, you know, the 4 bytes that represent the 4 axes and with the flags that we need to set into port B, all of them have that bit in bit 0 set, because ostensibly we should be disabling the mux, right? See, we load that into X, we then put that value into A, and it's branch if not equal, and then we store the A into port B, which disables the mux. See, decrementing means, you know, that bit that's been set in bit 0 becomes 0. That re-enables the mux, ostensibly because that's what you need to do for the DAC to get its value. We wait. Now if we're not going analog, we re-increment that, so that bit in bit 0 goes from 0 to 1, so we're back into disable mux mode again, because that's probably what you need in order to test a comparator, but that is not at all the case here. Here we never write to port B. For all this analog code, we never write back to port B. So port B remains in a state where the mux is disabled. Let's test a few games. Let's say we just decide to ignore and we just always read and always set the comparator bit. Does this, first of all, let's see, does this fix the games that we were checking? So we know how pole position works, right? It seems like there's still a little something going on there with the joystick. Like if I move just a little bit, I can turn a little bit, 1, then 2, then 3. See, there's like 3. And now if I go to the right, 1, 2, I only have 2 to the right, but to the left I have this one in between. So that's interesting. It seems that I'm not getting the full value to the right. So that's odd. I wonder. One thing we can check is when I'm pressing to the right, what is the value we're storing in the joystick input? Let's see, STL engine. Are we storing 128? or 127 anyway. Remap axis value. What are we doing here? Oh, it must be this one here. Or set axis. This one. No? Oh, sorry, because I'm not even attached. Right. That would make some sense. Debug, attach. Okay, so let's try and debug, because I don't have enough debug symbols in release. I might have to change this, but just want to see if my remapping makes some sense. Do I get the full extent of values that I expect? What I'm expecting is minus 127 to 127. It should be minus 128, but who cares, right? It should be fine. It's an approximation. That should be good enough. Value is 0, 0. Okay, let's do this differently. Let's go with update inputs. Printf joy analog values. Okay, let's try that again. I think what's happening is my printf is not printing. There we go. Okay, so we got some values. I think I need some spaces. Yep. Yeah, let's make these fixed positions. So let's say 0, 4D. So I'm kind of glad that like we fixed analog. I don't quite understand physically. I guess maybe I misread. Okay, so I push right, and then see up. Up we get 127, down we get minus 120. Yeah, so we don't get the full range. And I guess that's like some physical. Okay, there's minus 127. To the right is minus 127 to 127. Oh man, this mess here. Let me change that. Where was that again? That was in. I have a file to control this. Error handler. That's it. It's my policy. So let's just say ignore, so we don't get that spammage for now. Yeah, so I'm glad we fixed it, and I'll have to do a little bit more like looking into why and whether that makes sense. So that's 127, 101. But okay, so it looks like once we pass 64, we turn to the right a little bit. Then we pass 120 or so. Yeah, it looks like once we pass like 120 or something, we make this turn here. To the left, on the other hand, see minus 64 is the threshold for the first left turn, which is the same here. No, it's not. See, I can go up to 65 and there's no turn to the right. It almost feels like they purposely did something, like they added a left turn that doesn't exist on the right side in this game. Could that be? See, there's really 3 to the left. The first one's at minus 64, sorry. The next one is at around minus 120. And then there's a third one if I slam to like minus 126 or something. But not so on the right side. That's just, yeah, that could just be the game. Fascinating. was really cool. Well, let's try the other games now that we know use analog. So if we go back to our list, Solar Quest. Ships keeps turning. So for Solar Quest, let's go see if that's fixed. All right, we're not turning anymore. So I mean, that really did fix it. Nuke, thrust, fire. This is thrust. And this is... Alright, so this game works. Also a cool game that I've never played before. And finally there was Starhawk. Works, but aim input doesn't work properly. It keeps moving. So let's try Starhawk. Alright, so this works now. Oh, I wasn't pressing fire. Here we go. Here we can see that there might be a problem with the drawing of lines out in the far section here. It doesn't quite converge onto the back here correctly. I'm assuming that's not right. You ever die in this game? End. Yeah, so over here, the fact that it doesn't quite converge makes me think that that's probably a rendering bug. Curious. Starhawk, Vectrex. Oh no. You can see here actually that it's not quite aligned either in the real game. Although it does look a bit better. Yeah, but there's definitely a misalignment. It's too far to the left. This might just be the thickness of the lines. Like if we play a little bit, can I? Like if we play a bit with the thickness here. How does this work again? Thick baselines here. Yeah, definitely much more similar, just in terms of the way this looks. So that's kind of encouraging. One thing I noticed is that this overlay has this thick red line, like thick redness at the top, whereas it seems the real overlay doesn't have that at all. So this might be like a bad scan or something, I don't know. The bottom looks right, but the top not so much. So this is some kind of not quite accurate overlay. Okay, so you know, although I don't understand it, I am satisfied like with the fix. We fixed that problem. So let's do something here. Put some kind of comment about this. Okay, so analog input, I'm gonna put here note, or maybe a to-do or something. Looks like reading analog inputs doesn't necessarily require that the mux be disabled. If we look at the BIOS, what's it called again, the routine? Joy digital, no, Joy analog, let's say. Joy analog routine. When it reads analog values, it doesn't make sure to disable the mux, although it does so for digital for Joy digital. Seems odd. I'll just say try to figure out why this is the case. And then what I'll do is I'll just leave, whoops, that did not work as I thought. And I'll leave these this if and this const and all that stuff. I'll just leave this here because that's what it used to look like, and I think it's supposed to look like this. just to be more clear, it doesn't make sure to disable the mux before reading the comparator, although it does so for Joy Digital. Try to figure out why this is the case. Okay. Let's remove the optimize on and off. So you will say via fix analog joystick what can I say? Not correctly reading not working properly because comparator bit wasn't being set. C to do encode, but it looks like we don't need, looks like we must read joystick values regardless of mux enabled bit. So yeah, kind of strange. But now at least we can mark these off our list, right? Take that off. So input doesn't work. So let's say here this does work now, and I'm prepared to say that pole position works great. Solar Quest, we can say ship keeps turning issue. This one has graduated to great. We are greatness here. Works, but aim input doesn't seem to work properly. Okay, let's say we're golden. Awesome. Man, that's so great. At least those games work now. Here, let's actually commit the updated compatibility list. And that's the only thing. So when you make a change like this, it changes the entire file, even though, well, that's just what you get for markdown tables, right? So at least Beyond Compare sees what are the real differences, which are here. What was this? Okay, so we removed that. There's another one, Birds of Prey. I actually tested this one, but it worked, right? Okay. Okay, let's push this up, and I'm going to end the stream here, guys. So thank you very much for watching, and I'll be back next week on Monday, where we will continue to try and fix more of these problems with the commercially released ROMs. So yeah, thanks a lot, and I'll see you next Monday.